And just a little review what you actually talked about last year, but we talked about this unit as well. Let's just talk about all these transformations and what they mean. Good time to review. What's this? A outside, in front. Vertical. Stretch or compression, because we don't know what the value is. And the B stuck in here. Horizontal stretch or compression, again, just depending on the value. And the H. And that could be left or right, just depending on the value. And the very last one, up or down. Well, what we're going to do now is still work with this radical function, the square root, but we're going to do him as a transformation. So instead of using him as a base graph and then doing a bunch of stuff to him, he's going to be his own transformations. So we're going to start with sketching this graph, and then we're going to take what's called the radical of that graph, or the square root of that graph. So it's its own transformation. Way back in grade 10, how to graph a line. Who remembers anything about a line? Tell me anything you remember about a line. How do you know that? Mx plus b, and it is the b value. Tell me anything you know about lines. Ooh, tell me about slope. Okay, tell me about rise over run. But there's no number on the bottom, so does that mean there's no run? There's the imaginary one we don't know. Which, if you didn't have me last year in grade 10, why m? Why do we use m for slope? Okay, well, who invented this stuff? This is a unit you started in grade 10 that was called analytic geometry, which you probably didn't even pay attention to. If you look at my history of math poster back there, near the bottom, the second kind of picture from the left, you see a chef with a pot, and he's got two little pots sitting beside him. Casey, you can probably see it the best, or maybe Maddie. What does the big pot say? Analytical geometry. What do the two little pots say? Algebra and geometry. So that's what that guy did, was take algebra, geometry. So algebra is solving for unknowns, x's. Geometry is lines and shape, and dumped them together and made this analytical geometry. What was his name? Yeah, no, doesn't have an M at all in there. It's René Descartes is his name. He's a French mathematician. And so the story is that he was, well, we know this is true. He was very, very sick as a child, spent a lot of times in hospitals, a lot of time to sit around and think, and that's when he came up with most of his math discoveries. This part we don't know if it's true, but apparently he was staring at the ceiling. So look at my ceiling. But then I want you to actually look at my floor, because his ceiling was tiled in squares, not rectangles. So look down at the floor, because those happen to be squares. And he was watching a fly crawl along the intersections of these squares on his ceiling. And he thought, if we had some kind of system where I could count these tiles and there was a reference point to start from, I could do some pretty cool calculations. And so from that, what did he invent? The coordinate plane, right, with the x and y axis. It was him that came up with it, French mathematician. Well, that's why sometimes we call it the Cartesian plane. You might have heard of that. Cartesian, René Descartes, that's where it comes from. Who's taken French in the room? What is a map in French? A carte comes from him, because that's all a coordinate plane is a map. Well, the word slope means to climb a mountain, and what does the word to go up mean in French? Monter, that's why he picked M. Monte and Montagne. Oh, yeah, mouche for fly, maybe. No, but it was just the slope to go up. That's why it's an M, because the French invented it and they could pick whatever they wanted. Total sidetrack there, but kind of exciting. Not red pen, because this is not going to be our last graph. This is just our base graph. So we just talked, we start at 1 at the y-intercept. And because the slope is that -2 over imaginary 1 that we don't see, from that point I'm going to count 2 down, 1 over. And 2 down, 1 over, 2 down, 1 over. We use rulers because we're not barbarians. We are mathematicians. No snaggly little jaggly lines. Just repeating, what's different from these radical graphs from last unit to this unit is last unit they were a base graph and we did a bunch of transformations. Now it's its own transformation. I want to transform it to take the square root of this graph here. So what that means is take all the y coordinates and take the square root. So I'm going to start on the right-hand side. Kind of a y value I have down here is -8, for example. What's the square root of -8? It's the square root of -8. Can we take the square root of a negative number? Why not? Because somebody told us we couldn't? Why not? Why can't we do the square root of a negative? Yeah, you're right on. So you can't ever have the same number times exactly itself give you a negative. One of them would have to be negative, one would have to be positive. So there is going to be no graph where -8 is. Well, what about -7? Can I do the square root of -7? -6? What's the smallest value I can take the square root of? What's the smallest value I can take the square root of? Guess, just throw out a number. Doesn't have to be, because we can have decimals for square roots. We don't like them, but they exist. What's the smallest number I can take the square root of? Could I take the square root of half? So it's got to be less than 1. Could I take the square root of 1/4? 0. 0 would be my lowest number. So I want you to take your ruler and I want you to put it right on the x-axis. That is going to be the smallest value we can take the square root of. What that means is when we do this transformation of root of x, nothing under the x-axis is going to exist. It's impossible to have that when we do the square root, so it's not going to exist. So wherever you see the x-intercept, that's going to be our very first point on our new graph. Wherever you see the x-intercept, that's going to be our very first point on the new graph. Why does it not move? Well, what's the square root of 0? It's itself. It's 0, which is kind of nice. Put your ruler up at y equal to 1. Y equal to 1, which happens to cross right on the y-axis, which is kind of cool. What's the square root of 1? So it's also not going to change. It's going to be exactly the same on both graphs. Now, I probably don't want to use 2 because the square root of 2 isn't even. Do I want to use 3? What about 4? 4 is a really good point, so I'm going to look where it crosses at 4. And what's the square root of 4? So that point's going to drop all the way down to 2. So I didn't move it left or right. I just dropped it down to 2. What's the next good point that I want to use? 9. So I'm going to put my ruler up at 9. And the ruler is just to help you see where the line is. I'm going to take where that line is at 9, and I'm going to take the square root. It's going to drop down to 3. Okay. Didn't move it left or right, just dropped it straight down. Here is our radical graph of that line. Notice it still has that swoopy shape to it. Well, what we just graphed is actually this, because we took the square root of f of x. This is now a faster and easier way to do questions like we did like this last unit. What would we have had to do with this last unit? So what would we have to do with this -2? We would have had to factor it out. And so -2x squared divided by -2. And 1 divided by -2. Then we would have had to do the base graph and we would have had to identify the transformations. What would this negative have been? Horizontal reflection. Swoop would have gone towards the left. What would this 2 have been? Horizontal stretch. We would have grabbed it and yanked it out. What would this -1/2 have been? Horizontal translation, 1/2 unit to the right, and that's why this starts 1/2 unit to the right. What we have done is all of those transformations in like one step. Is that not just a little bit exciting? Like we just took a 4-step graph and just did it in one? So just a little bit of theory about what we talked about. Zero and 1 are always key points on these graphs. So if 0 and 1 are in the range of y equals f of x, what that means is they're y values. These points will, then these points with these y coordinates will lie on both graphs. They're the only points that's going to happen because they're the only points that are their own square roots. What's the square root of 0? What's the square root of 1? That's the only two numbers that happens. Any other number, you're not going to get itself back out. These are called invariant points. Invariant point. What does variant mean? Well, it comes from variable. What does variable mean? Changing. So what does invariant mean? Unchanging, not changing. Those are the only 2 points that are not going to change. So I want you to draw any line. I don't care the slope of the line. I don't care where it crosses through. Just draw a line. I know right away that where y equals 0 and y equals 1 is still going to be on my swoosh. Those are called invariant points. Wherever y equals 0 and y equals 1. So without doing much kind of math here, I know my swoop is going to go in that direction because it's got to pass through that 0 and it's got to pass through that 1. So I can get a pretty good idea of what the graph looks like just by knowing about the invariant points. The other characteristic you need to know is where the graph lies below the x-axis, wherever the original graph lies below the x-axis, the graph of the square root of x will not exist. Why? Because you can't take the square root of a negative number. Again, I want you to draw any line, and I'm going to draw a positive sloping line just because we haven't done one like that yet. Any line, I don't care what it looks like. What this property is telling you is everything under the x-axis will no longer exist. Anything under the x-axis will no longer exist on the root graph. Those are the two properties you need to keep in mind. 0 and 1 don't change. Anything below the x-axis will no longer exist. So here's a standard radical question. Given the linear function below, so instead of making you draw it, they've given it to you. We're going to draw root of f of x, and then somebody remind me about domain and range. These are some of my favorite graphs to draw, because you're not going to believe me that it's actually this easy. I'm visual, so the first thing I do is I grab my pencil, and anything under the x-axis, I cross it out. You don't have to cross it out. It's just visually for me to remember it's not going to exist on the new graph. Anything under the x-axis is gone. Then I take my ruler and I put it at y equal to 0. And you don't need to use your ruler. It's just visually for me. I look, where does it cross the x-axis? So where is y equal to 0? And I put a dot there. Then I come up to wherever y is 1, and I put a dot where the graph at y is 1. Again, you don't need to use your ruler. It's just a visual cue for me to figure out where is 0 and where is 1. Now you just need to figure out which way does the swoop go. Does it swoop to the left or does it swoop to the right? Well, it swoops in the same direction the line is going. If the line is going towards the left, bam, we're done. That's it. Swoop to the left. If the line went the other way and went towards the right, I would swoop to the right. Bam, radical graph done. Is that not awesome? Just a little bit. Again, you don't have to cross this out. This is just for me, the way I remember that it doesn't exist. I mark the 2 points, swoop it in the right direction, we're done. That's it. That's a root graph. How freaking awesome is that? Domain and range. The left, the arrowhead means forever and ever and ever. We come to the right. Where is that point going to be? Well, we're going to have to estimate it a little bit. Somewhere between 0 and 1. 0.5, I think pretty close. So how do I state all the points from negative infinity to 0.5? Two different ways, pick whatever one you like. Give me either one of them. I like that. The other notation, if you like it better. Negative infinity, 0.5. What kind of bracket on the 0.5? Square bracket. There's no graph under here because we crossed it out, so that helps with the range. What's the lowest possible value of the range? 0. Arrow going on forever means the highest possible value is infinity, so y is greater than or equal to 0. If we want to match this guy, we're going to have 0 to infinity. Anything under the x-axis gone? Again, you don't need to cross it out. I just like to do that in my head so I remember it's not there. Then I come first where y equals 0, and I put a dot wherever it crosses the x-axis. You don't need to use the ruler. It just helps my eye figure out where the line is. Then I come to wherever y is 1, put a dot wherever the graph crosses y at 1. Just to repeat, why are we using 0 and 1? Why are those our key points on the graph? They don't change. They're called invariant points. They're the same. Then you're just figuring, swoop to the right or swoop to the left? Well, which way does the line point? Towards the right, so I'm going to come through these points and swoop. It is pretty fun. It's going to stay not quite this easy, but it's going to stay pretty easy. Write down the domain and range. An estimate for this value here? 0.75, yeah, 0.6. As long as it's bigger than 0.5, I'm okay with that. So I'll say 0.75 to infinity. If you like the other notation, x is greater than or equal to 0.5. The range, or 0 to infinity. That was pretty sloppy. Well, that was lines, but we know lines aren't the only kind of function out there. Hello, parabolas. We're going to do the same thing. Start by drawing the parabola, then we're going to take the square root, then we're going to talk about what the characteristics are. Good time to review, how do we graph a parabola? What are the 3 pieces of information you need to graph a parabola? Vertex, width, direction. What's the vertex of this parabola? Offer of 0, -4. Looking for confirmation. The width. Confirm. The direction. Confirm. Okay, let's draw the parabola. So 0, -4. Up 1 over 1. Up 1 over 3. Over, I did that backwards. Over 1, up 1, over 1, up 3, over 1, up 5. The number inside brackets, change the sign. There isn't one, so it's 0. Number at the end, leave it alone. So this is really our horizontal translation and our vertical translation is where it's coming from. I'm going to do exactly what I did with the line. Anything under the x-axis is gone. Anything at 0 and 1 are going to be invariant points. So anything under, bye-bye. So that whole section of the graph is gone. Can't take the square root of it, so it's not going to exist. I'm going to put my ruler at 0. Anytime I see graph, I'm going to get a point. Last time we had 1. This time we have 2. We have an x-intercept on the left and an x-intercept on the right. I'm going to go up to 1, do the exact same thing. This time we have 2 points where it crosses, one on the left, one on the right. What's going to be the difference between a linear radical graph and a quadratic radical graph? A double swoop. This one's going to swoop to the left, and the other side, swoop to the right. There's what a quadratic radical graph looks like. Double swoop. It says compare the domain and range. So we'll first do the parabola. Then we'll do the square root of the parabola. Now what's going to happen at the beginning, when you see a question like this, your brain is going to want to freak out. Because you're going to be thinking transformations, because that's what we spent 2 months now doing. And you're going to go, what do I do with this with transformations? I don't know. I don't know how to draw the base graph. What is the base graph? So if your brain is starting to go, what the heck is going on? It's a radical question from this unit, not a transformation question. You can do this with transformations. You're just doing a lot more steps. This is just a radical graph. Graph the parabola, mark your points, do your swoops. Domain of the original parabola? That you're thinking range, you want to think left and right. Remember last year, I was like, this is the idiot point because the parabola is always going to have the same domain forever and ever and ever. Yep, it's always XER for parabola, unless it flips sideways. Range would be y is greater than or equal to -4. I drew a what now? Oh, thank you, thank you. Okay, well, what do we do now when it's in pieces? Well, we just do each piece separately. So I'm going to look at this left swoop first. What's the lowest value if it's got an arrowhead on this way? Negative infinity. What's the highest value? What's the value of the x-intercept? -2. So the domain for the left-hand side is x is less than or equal to -2. And then I'm just going to do the right swoop separately. The lowest value is 2. Highest value is infinity. So x is greater than or equal to 2. Grab my red pen just for the first one. I'm going to put a U in between. And it's a very particular U because it's a symbol. It's not actually the English letter U. Does anyone remember from last year? What does the U mean? Okay, so we'll make a note. The name of this symbol is called union. Not onion, like one of my students thought last year and wrote that on the exam. It's not onion, it's union. Union. What it means in English is and. It's the math way of saying and. So we're saying the domain is all the values less than -2 and all the values greater than 2. Range again, I'll do separately, so just look at the left one first. What's the lowest value? Zero. What's the highest value? So y is less than or equal to 0. Greater than or equal to 0. Okay, look at the swoop on the right. What's the lowest value? 0. Highest value. Do I need to write it again? No, we don't need to. No, we don't like redundancy. That's it. Y is greater than 0 or equal to 0. Do you get this, that why it's in pieces? Why there's 2 sections in the U? Remember, not onion, union. Just more more practice with the parabolas. So now we're going to do negative 2x squared plus 9. Vertex. I heard a really quiet 0, 9. Direction. Why is it down? And we now know what is that negative in terms of transformations. Why is it flipping it down? It's a vertical reflection. That's why the direction changed last year. The width, standard width is 135, dot, dot, dot. But oh no, what do we want the width to be? Why? And in terms of transformations, you now know this is a vertical stretch. That's why we're multiplying by 2, because it's a vertical stretch. Okay, draw me the parabola. Very rarely do we actually have to count that 10. Same steps every time. I take whatever's under the graph, I cross it out. Again, you don't have to cross it out. It's just for visual people. It reminds us it's not there, it's gone, it doesn't exist. Wherever y equals 0, I mark those points. Wherever y equals 1, I mark those points. Now this one's going to be a little bit different. It's not going to be a swoop to the left and right. Why not? Because it's coming in towards. So all I'm going to do is just grab the vertex, and I'm going to actually do the square root of the vertex just to figure out what's happening. What's the square root of 9? So there's going to be a point here at 3. So I'm just going to write where that came from, so when you look back, it came from the square root of 9. So this one's going to be like a little hill. So if it's an up pointing parabola, you get the double swoop. If it's a down pointing parabola, you get the little hill. Okay? Up parabola, you get left and right swoop. Down parabola, you get the little hill in the middle. And again, the vertex point will always just come from taking the y value and square rooting it. Write down the domain and range of the radical, so just the red graph. We have a teeny tiny little problem with the domain. What are the values that it crosses at? Is it negative 2 and 2? Is it negative 2 and 2-ish? Well, ish isn't good enough for a mathematician. If ish isn't good enough for your surgeon, it's not good enough for a mathematician. Would you like a surgeon to know exactly where to cut you, or ish where to cut you? So when you're given the function, we need to actually calculate the x-intercepts. When you're given the function, we need to calculate the x-intercepts. We spent a whole unit on this in grade 11. How many ways are there to solve a quadratic? Factoring. Completing the square, which is factoring. Factoring, completing the square. Graphically, which is using your calc. Rhymes with difference of wares. Difference of squares. And the last one, which may be up on the wall over there, the thing that you hate, that makes you cringe, quadratic formula. So again, I'm going to repeat, when you have the actual equation, ish isn't good enough for the intercepts. We need to actually calculate them. I'm going to make the left-hand side equal to 0, keep the right-hand side exactly the way it is. For this method, factoring isn't your best method because you got 2 and 9, which aren't going to divide evenly. What's the best method for this particular equation? I don't like to quad formula. It's busy. I don't like it. If I can avoid it, I do, so I'm not going to pick quad formula. Let's pretend it's a non-calculator question, so that method is out. So what does that leave us with? What are the 5 methods for solving a quadratic? Okay, we got complete the square, and we got, well, I just said factoring is not going to be great because the 2 and the 9. Square root. Which one's going to be the easiest for this one? It's square root. Square root's going to be the easiest for this one. I'm going to take the 9 over to the other side. How do we get rid of plus 9? Minus 9. How do I get rid of a coefficient of negative 2? Divide by negative 2. How do I get rid of a squared? So what's the opposite of squaring something? Square root. Grabbing my red pen, what was the thing we preached over and over and over last year? Whenever you put a square root, what has to go? Plus and minus. Okay, what do I do with this crap that's on the other side? Well, if we can square root it, we do. If we can't, we leave it. So we do the numbers independently. Can I take the square root of 9? Yes, it's 3. Can I take the square root of 2? No, I leave it alone. But wait, we don't like that radical on the bottom. Remember unit 2 when we were like, we're just fussy people, we don't like it? How do we get rid of a root on the bottom? Anyone remember what that's called? What's the process called? Abby, you did a poster on it. Patsiana, you did a poster on it. Mikhail, you did a poster on it. Rationalization. So I'm going to times by root 2 over root 2 to get rid of that 2 on the bottom. The top's going to become 3 root 2, and the bottom's just going to become 2. That makes a mathematician happy. That's not ish, that's the exact x-intercepts. So we're going to use that for the domain. The lowest value is our negative 3 root 2 on 2. Highest value is our positive 3 root 2 on 2. What's the notation for between those numbers? Less than equal to x, less than equal to. If you like the other way with the brackets, use the other way with the brackets. I'm going to put this in a highlighter bubble just so to draw attention to it. There's no ish when you have the equation. If you just have the graph, you can ish. If you have the equation, you need to give me exact x-intercepts. Would you like your nurse to give you the exact dosage of medicine you need, or ish? Right? There's times exact values matter. There's times we can estimate it. What about the range? This is where we breathe. We're like, yes, we can actually just get the values off the graph. What's the lowest value for the range? And what's the highest value? 3. It's always that domain that's the tricky one. Questions so far? That's why I say the unit gets a little bit harder, because it brings back the stuff from last year. Last one for today. Another parabola. Sketch the graph of x squared plus 4x plus 2. Then we're going to do the radical. Then we're going to state the domain and range. Vertex. Oh, can we tell the vertex from this guy? No, what do we need to do? Make it into the other form, and what's that called? What's that process called? We already talked about it today. Completing the square. Completing the square. Good time to review completing the square. See how everything from last year is coming back this year? So completing the square is where I keep the x squared and I keep the 4x and I push that 2 off to the side and I ignore them for a moment. I need to fill in a number here and I need to fill in a number there. The first number is the number that's going to make this a perfect square trinomial. Anyone remember how to get this number from last year? Middle divide by 2 and squared. So 4 divide by 2, 2 squared plus 4. And I'm just going to put the work for this one, although you wouldn't need to show it. But I don't want you to look back and think we just copied that 4. So it was 4 divided by 2 squared. If that number's 4, what's the number at the back? Minus 4. Why? To balance it out, right? We can't just add a number to an equation. We have to balance it out with the other side. Then we take the first 3 and we factor them. We take the last 2 and we just combine them. I'm looking for a binomial squared. Anyone remember how to get the binomial from this guy up here? X plus 2, so that comes from middle divide by 2. And then we just combine these two together, plus 2 minus 4, negative 2. That only took 2 days to teach the first time. Look at that. Vertex. And again, that's why we need to complete the square. You need to be really good at math to be able to look at this in the question and know the vertex is negative 2, negative 2. Direction? Up, how do you know? There's no negative, there's no vertical reflection. And the width? 135. So negative 2, negative 2. 1 over 1 up. 1 over 3 up. Is it going to be a double swoop or is it going to be the hill? How do you know? Up. So I'm just going to write for visual people. If it's an up parabola, you get the double swoop. If it's a down parabola, you get the little hill. That now kind of looks like an angry face. Stuff under no longer exists, it's gone. Mark your points where y equals 0. Mark your points where y equals 1. Swoop to the left, swoop to the right. Domain. What do we need to do in order to find the domain? We need to find the x-intercepts. Again, ish doesn't work with this. How do we solve a quadratic? Completing the square? Factor? Quadratic formula? Square roots? Yeah, and graphing. Good job. Well, take a look. We've already completed the square. So it's going to be easiest just to take this and do square root. So I'm going to put 0 equals x plus 2 squared minus 2. How do I get rid of the minus 2? Add 2. How do I get rid of a squared? But what has to go in front of it? So that gives me plus or minus root 2 equals x plus 2. Minus 2, and where does it go with all this stuff? We talked about this last year. Where do I put it? We just tuck it in front and then follow by that plus or minus root 2. So I'm just marking on the graph just so you can see later. This one has to be the minus 2 minus root 2. And the other one has to be minus 2 plus root 2. A smaller one has to be on the left, bigger one has to be on the right. Okay, the domain, because we have two swoops, we're going to do two pieces. So if I just look at this one, I've got x is less than or equal to negative 2 minus root 2. The other piece on the right is going to be x is greater than or equal to negative root 2 plus 2. What's the symbol that goes in the middle? Union. Just means and. And then range, we're always like, yeah, let's work for the range. What's always the lowest value for the range? 0, so it has to be y is greater than or equal to 0. It's always that domain that's so much work.